Alright, welcome back. In this video we're going to talk particularly about the second derivative and how we can use concavity to determine if a critical number has a relative maximum or a relative minimum. So let's take a look at a function that has a relative maximum. At this point right up here, we know we have a critical number, a place where the derivative is 0. Now we're not dealing D and E, no D and E's. We just want a horizontal tangent. So we want to know if this critical number here is a relative maximum or a relative minimum. And of course, obviously it's a maximum because the slope is going from positive to negative. But also notice this is a function that is concave down. And if we have a function that is concave down, we can say something about our critical number. So we can say that this has to be a relative maximum. So we can say if we have a critical number and we know the function is concave down, we're going to have a relative maximum. In other words, our critical number has to be the highest point. Likewise, well, what if I have something that is concave up? Same thing. Here I have a critical number that is 0, where the slope is 0 at the very bottom of a horizontal tangent. But notice, this time the function is concave up. Well, if something's concave up, that critical point, the lowest point, has to be a minimum value. So our critical number has to be a minimum value. So we can say if we have a critical number and the second derivative is greater than 0, we will have a relative minimum. And that's a very useful tool for us. So let's see here. We want to determine if the vertex of this parabola is a relative maximum or a relative minimum. So we have to find the vertex of our parabola. Well, this is just where the slope is 0. If you think about the parabola, it's where the slope is 0. So I can find that. So I take my first derivative. That's going to give me negative 2x plus 4x. Whoop, plus 4. That's embarrassing. Plus 4. And I'm going to set that equal to 0. And I get x equals, what's that? 2. So what we want to find out at x equals 2 is this parabola going to have a relative maximum or relative minimum. So for our test, we're going to take the second derivative. And if you notice, the second derivative is negative 2. So it doesn't matter where we plug it in, it's always going to be negative, which is always less than 0. So that's telling us that this function is concave down. Whoops, therefore we should say f is concave down here. So if I know something is concave down, this has to be a relative maximum. And that's what we're going to say. F is concave down. Therefore, the vertex x equals 2 is a relative maximum. Be very careful. The big thing, people say, oh, it's less than 0, it's concave down, it has to be a minimum because we think less than 0 as a minimum value. But that's telling that the function is concave down, which means that the critical number at the very top has to be a maximum. And there's our answer right there. So let's take a look at what the second derivative test actually tells us. If a function is let f be a continuous function, and the second derivative must exist. So first thing that they're telling me is that we have to have a critical number. The slope is 0. In other words, we only want a horizontal tangent. Now, in other words, no cusps or corners. They don't count. Only horizontal tangents. If the first derivative, oh, this is terrible. This should be the second derivative. Let's fix this. If the second derivative is greater than 0, then f has, so if the second derivative is greater than 0, it's telling us that we are concave up. We are going to have a relative minimum. If the second derivative, it's embarrassing. If the second derivative is less than 0, well, then we know that that's going to be concave down. Well, that's going to be a maximum value. So we'd have a relative maximum value right there. Now, here's the problem. If the second derivative is 0, then f has a relative I don't know. We really don't know what that is because it's not a maximum or a minimum. It's not going to be either one. If the second derivative is 0, we really don't know what it is because there's no concavity at that point. It's not concave up or down. I don't know if it's concave up to give me a minimum or concave down to give me a maximum. We really don't know. So in this case, here's what we're going to do. We do the first derivative test. What's the whole point of the first derivative test anyways? To determine if a function has a relative maximum or a relative minimum. So a lot of times for the second derivative test, we really don't use it that much other than to determine what's the concavity of a graph. We really don't like to use it for relative maximum mins if the first derivative test will work just as well. So a lot of times on the homework, it'll say, if possible, use the second derivative test. So let's talk about this. So we want to find the relative maximums and the relative minimums for the following graph. So, ready? I'm going to do the first derivative test. So, first derivative, I got to get my critical numbers first. First derivative is easy, negative 15 x to the fourth plus 15 x squared. If I set this equal to 0, I can factor out a negative 15x squared. Negative 15x squared, and I'm going to get x squared minus 1 equal to 0. And I would get my critical numbers are 0 and plus or minus 1. Now, if I do my second derivative test, let's do the second derivative test. If we try the second derivative, whoops, can't spell today, the second derivative test, let's plug that in. The second derivative would be negative 60x cubed plus 30x. Well, let's just plug in the 0 just for fun. That's going to give me 0. And up here, that's not really telling me anything. If I plug in 0, I'm not really given any information there because it's not concave up, which would tell me it's a minimum, and it's not concave down, which would say it's a maximum value. So this is an I don't know, an IDK. We really don't know what that is. So my rule says, well, if it fails, we're just going to use our first derivative test. So that's what we're going to do here. We're just going to set up our first derivative test, which we've done 100 times. We have 0, negative 1, and 1. And I'm going to plug it in. I'll plug in something like negative 3. If I plug in negative 3 into my derivative, remember this is negative 15x squared minus 1. This first one's going to be negative. Negative 3 squared is 9 minus 1. That's a positive, so this is going to be a decreasing function. Now, at the 1, there is no multiplicity, so I know that this is also going to be negative. Now, if I'm good, notice there is multiplicity here. What that means is at 0, if one side's negative, the other side has to be negative as well. And if you're really good, you probably recognize that I made a mistake here. So let me go back and fix this. I'm going to delete all the evidence here. If I were to plug in negative 1, remember there's no multiplicity at the negative 1, which means if this was negative, this has to be positive. It has to be going up. Now, the multiplicity is at the 0, which means if this side is positive, this side has to be positive. Well, also increasing. And the 1, you're going to find out it's going to be negative as well. So it's decreasing. So now I can find out my relative max and min. Look, I have a relative minimum at negative 1. So we can say f has a relative minimum at x equals negative 1. And that is because the derivative, the first derivative, goes from negative to positive. And f has a relative maximum at 1. And that is because the derivative, the first derivative, goes from positive to negative. Right there. There's our answer. All right. So let's take a look at one where we would really like to use the second derivative. And normally for triggerlicious functions right here. So we want to find the relative maximums and minimums for this function, 2 cosine x plus sine of 2x. So the first thing we have to do, we have to get our critical numbers. So we're going to take that function's derivative. We get negative 2 sine of x plus, be careful, the derivative of sine is cosine, 2x. There's a chain rule right there. So multiply that by 2. Set this equal to 0. I can factor out a negative. I can factor out a negative 2 here. Once we set this equal to 0, we do have to change a little bit because I can't solve this. So I'm going to replace this. I can write this as negative 2 sine of x plus cosine of 2x is an old identity. 1 minus 2 sine squared of x times 2. And let's see, if I can simplify this out, we would get, if I write this in the right order, we would get negative 4 sine squared of x minus 2 sine of x plus 2. And I can factor and divide everything by negative 2 might help me a little bit. We're going to get 2 sine squared of x plus sine of x plus 1. And this I can factor. We're going to get 2 sine of x, sine of x, and let's see here. Sorry. This should be a minus 1, because if I'm dividing by negative 2, right? When we're dividing by negative 2 there. 1. And I want to get this to be positive, and this one will be negative, I believe, right there. So let's take a look here. I want to make sure we get positive sign. So plus 2 minus 1 sine of x. Yep. And if I set these equal to 0, we get sine of x equal to 1/2, and sine of x equal to negative 1. Solving these, we get x where sine equal to 1/2, or sine equals at pi over 6, and 5 pi over 6, where sine equal to negative 1, that's 3 pi over 2. All right, there we go, our little triggerlicious values. Now, I could do my first derivative test here, and I would be fine with that. But let's apply what's called our second derivative test. So when we do our second derivative, ready? We already got our first derivative. We're going to get negative 2 cosine of x minus, be careful, this becomes sine of 2x times 4. Remember, I'm already multiplying by 2. I just got to do another chain right there. And that's where we get that 4 right there. And this is what I want. Now, the reason why I would prefer to do this than do the second derivative test, that's not so much fun to really work with right here. That's not really fun to work with in terms of my sign charts. So now all I got to do is test out my points. Ready? If I were to plug in pi over 6, let's do this real quick, negative 2, the cosine of pi over 6 is root 3 over 2, minus, this becomes the sine of pi over 3. Well, it becomes 4, and the sine of pi over 3 is root 3 over 2. So no, I don't know what the answer is, but I do know that this is negative. So therefore, what can I say? This is concave down. So we have a relative maximum. So we can say x equals pi over 6 is a relative maximum, and that is because the second derivative at pi over 6 is less than 0. The function's concave down. And I can do the same with all of them. What about the second derivative at 5 pi over 6? Plugging that in, here's my first derivative. We get negative 2. The cosine of 5 pi over 6 is going to be negative, so that gives me a negative root 3 over 2 minus 4. The sine of 5 pi over 3, that's negative also, negative root 3 over 2. And notice, two negatives, these all become positive or greater than 0, so this is concave up. So we can say x equals 5 pi over 6 is a relative minimum because I'm at the bottom there. See, I draw it out. It doesn't take long. Draw it out. It's a relative minimum, and that is because the second derivative at 5 pi over 6 is greater than 0. And then on our last one here, oh no, I ran out of room here. Let's see here. If we plug in 3 pi over 2, that's not that bad to do. Go to your first second derivative. The cosine of 3 pi over 2 is 0. So this just becomes 0 minus 4. This becomes then the sine of 0, the sine of 3 pi, which is also 0. No, I get a 0. And automatically I run into my main issue, which is what we had before. We don't like this to be 0. So let's see what's kind of going on right here real quickly. If we were to plug in the 0 here, my second derivative, and let's see here. I know my other critical numbers are at pi over 6 and 5 pi over 6. Now, I can use this to kind of help me. Let's take a look here. Remember, at pi over 6, what did we say the concavity was? We said it was concave down. At 5 pi over 6, we said it was concave up. I can use my slopes here. Notice, here it's a positive slope to a negative slope. So I can say that this is positive, so this is going to be concave up, and this is going to be negative slope. Sorry, we're not using that. We're using the first derivative test here. Just got all confused there, confuddled. We're using the first derivative test here. So this is a positive slope, it's increasing. Here we have a negative slope, so it's decreasing. Here, the slope is negative, so it's decreasing as well. And at 5 pi over 6, here we have a positive slope. It's going up. So notice at 0, there is none. So we can say, therefore, we can say at x equals 0 is neither. And that's what we're going to put. X equals 0 is neither. All right. So hope you enjoyed that video. I will see you all later. Bye-bye.